Welcome back to this lecture series on pulse width modulation for power electronic converters. We have been going through different course modules. We looked at an overview, first had an overview of various power electronic converters, then we looked at the applications of voltage source converters, then we looked at purpose of pulse width modulation, then we slowly looked at pulse width modulation at low switching frequency. With very low, like such like a couple of 1 or 2 switching angles per quarter, very few switching angles in a quarter. And in the subsequent 2 modules, we are looking at PWM generation at a fairly high switching frequency, where the switching frequency is much higher than the fundamental or the modulation frequency. And if there are 2 popular approaches, we looked at both the popular approaches of producing PWM. One is triangle comparison, other one is the space vector based PWM. And in the space vector based PWM, we saw that the space vector based PWM is more general than the triangle comparison based PWM. So, you have continuous and discontinuous modulation methods, which can be implemented either using the triangle comparison approach or the space vector approach. You also have certain advanced bus clamping PWM methods, which can only be implemented using the space vector approach. And now, after the PWM generation, we have begun to look at the waveform quality. Well, we are producing PWM waveforms, all right. We are able to control the fundamental voltage. The purpose of the PWM is twofold, one is to control the fundamental voltage, and the next is to control the also have a reasonably good waveform quality, that is make sure that the harmonics and their harmful effects are reasonably low. And so, we are getting into this of analysis of line current ripple, which is what we have been focusing in the present module now. So, actually the present module, the analysis of line current ripple includes a set of things, these items or topics. So, one of them was we had a review of the PWM techniques, which we had seen in the last 2 modules, and we looked at the DC bus utilization, that is how much fundamental or AC side voltage can be produced with a given DC voltage. And we looked at the harmonic spectra, typical harmonic spectra of the different PWM waveforms when you are employing different PWM methods, sinusoidal PWM or conventional space vector PWM, etc. We developed some idea about that. And as I told you that our focus is not so much on the harmonic spectra, and I also gave you some references where the harmonic spectra are discussed in much greater detail. And we looked at the harmonic model and the total harmonic distortion factor, etc. And the harmonic model, as you can quickly recollect, it is actually for for an induction motor drive, the harmonic voltages see the induction motor as its leakage inductance. So, that is the harmonic model. And then this is a measure of the waveform quality. We looked at the total harmonic distortion factor, which is basically what is the RMS current divided by the fundamental current. So, one way to come up with this total harmonic distortion factor is to calculate the individual harmonic components, and then of the voltage. And from the individual voltage harmonic components, you can compute the individual current harmonic components, and from there the RMS current ripple, and hence the total harmonic distortion factor. What we have been doing is the other way, that is we consider the error voltage vector. The error voltage vector is a representative of the harmonics and the voltages. Now, you integrate that error voltage vector, and that is what is the stator flux ripple vector, which is a measure of the current ripple vector. So, since the harmonic model is that of an inductance, so if you apply voltage across an inductance, there is certain current through the inductance. The current through the inductance is proportional to the integral of the voltage applied. That is why if you have error voltage vector and you integrate that, and you get your stator flux ripple vector, or equivalently your current ripple vector. And so, we would kind of review these 2 things which we discussed in the last class, error voltage vector and the stator flux ripple vector, and we would focus on how the RMS line current ripple over a subcycle, and also the RMS line current ripple over a sector or the line cycle. So, sector is 1/6 of the line cycle, and we are also going to look at the influence of the switching sequence on the RMS current ripple, and how you can construct hybrid PWM techniques which use a combination of switching sequences, that we will do in the next lecture. So, now we will be focusing on the calculation of RMS line current ripple. So, today we are going to look at evaluation of RMS line current ripple using the notion of stator flux ripple. As I mentioned just a while back, this RMS line current ripple can be evaluated from the harmonic spectrum also. You can calculate the voltage harmonic components and from the voltage harmonic components you can calculate the current harmonic components, and from the current harmonics you can evaluate the RMS current ripple. On the other hand, what we are going to do is we are going to use the notion of state efflux ripple. What is state efflux ripple? Is the time integral of the error voltage or the voltage ripple. So, we are going to use this to evaluate RMS current ripple primarily in this lecture. So, here there is a quick review of a voltage source inverter. So, there are 3 legs corresponding to the 3 phases. In each leg you have 2 devices which switch in a complementary fashion, and if essentially everything is a single pole double throw switch, and the midpoint is what we call as pole, and we generally say pole voltage. We are talking about the voltage at this midpoint with respect to the DC bus neutral O. So, we are looking at 3 phase loads. This R, Y, B are the midpoints of the load terminals. They are connected to the midpoints of R phase leg, Y phase leg and B phase leg, and N is not connected anywhere particularly. So, the R, Y, B are the ones that are connected. So, this is something what is called as an isolated star connected load with isolated neutral. So, sometimes you may have 3 phase 4 wire connections where the neutral is also connected somewhere. Here what we are talking of is a 3 phase 3 wire system load. So, this is the kind of load, and these are the different voltage vectors, and since you had there are every phase is positive or negative, that is every phase is like a single pole double throw switch. It can be either connected to the positive throw or to the negative throw. If you look at R phase, it is all positive here and it is all negative here. Similarly, here it is positive, here it is negative. So, R, Y and B can be either connected to positive or negative, and therefore, there are 8 inverter states as we discussed before, and of these 2 inverter states produce the null vector as we discussed earlier. Then the remaining 6 states produce the 6 active voltage vectors. Now, then you can in the space vector based modulation, what you do is you have a revolving reference vector. This revolving reference vector, it revolves at the fundamental frequency, and its magnitude is indicative of the magnitude of fundamental voltage that you want, and you sample it in every sub cycle. Once you sample it in a sub cycle, you produce it using a set of the nearest vectors. So, let us say you have sampled, and that sample lies between these 2 vectors, active vector 1 and active vector 2. As you can recall, we will apply active vector 1 for some t1 seconds and active vector 2 for t2 seconds, and the null vector for the remaining tz seconds to produce an average voltage vector equal to this reference vector. So, that is what is illustrated in this diagram, and when you are doing that, how you are going to calculate your T1, T2, Tz is what is discussed here. So, this is the reference volt seconds and this is the applied volt seconds. The reference volt seconds should equal to the applied volt seconds, and the subcycle duration, within the subcycle you apply 3 different vectors, active vector 1, active vector 2 and the null vector. So, their times add up to Ts. So, you have 2 equations here being a vectorial equation, and this is a third equation. There are 3 equations and 3 unknowns T1, T2 and Tz. You can solve for them as shown below here, and you can calculate your T1, T2 and Tz. This is what you do in all space vector based PWM. Particularly when you are talking of the conventional space vector PWM, you have this null vector time Tz, and there are 2 different 0 states 0 and 7. So, what you do is you apply the 0 state 0 minus 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 for half the time and plus 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 for half the time, that is Tz by 2, and here it is Tz by 2. You start here with minus minus minus, let us say stay here for Tz by 2 and switch the R phase to go to active state 1, stay here for t1 seconds, and from here you switch the Y phase and go to active vector 2 plus plus minus, you stay here for t2 seconds, then switch the B phase and you can go to the 0 state plus 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 for Tz by 2. You can do the same thing in the reverse fashion in the next subcycle. So, you can do this in the alternate fashion, and this is what you call as conventional space vector PWM. Similarly, when your reference vector it moves moves and goes to the next vector instead of vector sector. Now, this is called sector 1, it would move to sector 2. When it moves to sector 2, instead of active vectors 1 and 2, you will start using active vectors 2 and some other vector 3, which will be like this. You will start using that, and this is conventional space vector PWM, just for your recollection. Now, we are going to be dealing with the calculation of RMS current ripple exclusively for conventional space vector PWM today, though the process is quite general. You can use the same process for the other PWM methods also, which is something we will discuss in the next class. So, today the focus will be on RMS current ripple, particularly for this conventional space vector based PWM. So, you can probably take this as an illustration of how to calculate RMS current ripple with the space with conventional space vector PWM as an example. So, let us move on. So, this is to, this is to review error voltage vector that as I said before. So, there is something there is always a difference between what we want and what we can apply in the context of this inverter. So, what we want is a sinusoidal voltage, but you do not get this. So, what you do is you actually synthesize sinusoidal voltages by applying DC pulses, that is what you do in an inverter. So, instead of a sinusoidal voltage you keep on applying DC pulses, positive and DC pulses. The same thing if you look at it in the space vector domain, you have this reference vector. So, applying 3 phase sinusoids means applying a voltage vector of constant magnitude and revolving at a uniform speed in the space vector domain. So, we are showing this reference vector here at a particular snapshot of the reference vector or a particular sample of the reference vector now. So, this is the reference vector. So, in a particular subcycle this is the commanded reference vector, you need to produce this reference vector. How are you supposed to produce this reference vector? This VREF vector is not available to you. The closest options available to you are V1 vector, V2 vector and Vz vector. Though V1 vector and V2 vector are close to this, both in terms of magnitude and angle, they are not equal to them, they are different from this. So, this null vector is also substantially different in magnitude from this now, right. So, what do we see? So, what are we doing? We are producing this VREF vector in an average sense. We are doing it in an average sense by applying this for certain time t1 and this for certain time t2 and this for certain time tz. So, there is a difference between what you apply and what you want. Now, what I want is VREF, but what I apply is null vector. That is the particular example that I am considering. What I am applying is null vector and therefore, there is an error vector. What is that error vector? The error vector is applied vector minus the desired vector, which is minus VREF vector. So, let me just write it down quickly. So, you have this V error vector here is equal to minus V ref vector. So, this is what we have now. So, we can look at it in the DQ domain also. This is I have just generally written it in the in the polar coordinates. I can write this in alpha beta. I can also write it in the DQ domain, right. So, this is what the DQ domain is what we discussed in the last class. What we can do is we can do the analysis in instead of alpha beta axis in D and Q axis, which this is D and this is Q, both are revolving at fundamental frequency omega, where omega is the fundamental frequency now. So, there is an error voltage vector. This error voltage vector can be resolved along Q and T axis. Obviously, you can see that the error voltage vector is entirely aligned along the Q axis. So, you can say VQ tilde is equal to minus VREF and VD tilde is equal to 0. So, these are the components of the error voltage vector when 0 vector is the applied vector now. So, sometimes you apply the 0 vector and sometimes you apply active vector 1 or active vector 2. Now, let us say you have applied the active vector 1. Therefore, what you have applied is this, what you want is the reference vector and therefore, there is an error between the two and that is what is given by this V error vector now. So, what is this V error vector in this case? V error vector is equal to V1 vector, which is minus VREF vector. The other way I can write it is V1 vector is actually this is VDC angle 0 degree in the alpha beta plane like in polar coordinates and minus V reference angle theta s as written here now. So, I can write this in the VQ in the DQ reference frame also. If I take VQ tilde, now what is VQ tilde? It is going to be VDC times cos theta s minus V reference. This is your VQ tilde. And what is VD tilde? There is VDC instead of cos, it is going to be sine of 60 degree minus theta s. That is going to be your VD tilde, right. So, these are the error voltage vectors when your reference vector is what it is as shown here and the applied voltage vector is 1. This is the error voltage vector. The components of the error voltage vectors along the Q axis and D axis are as indicated below. Now, we have covered the case of null vector, we have covered the case of active vector 1, and the only thing remaining is the active vector 2. So, now let us say look at the active vector 2. So, let us go to this active vector 2. So, here what we have is again let us see that we can consider this your q axis and this is the d axis, and both these are revolving at omega, but now you are considering a snapshot, that is they revolve at the fundamental frequency. Your sampling time is much shorter, is smaller than the fundamental frequency. So, you can say your V reference vector is aligned with the q axis, and then this is your d axis now. So, your error voltage vector is the applied vector is this is the applied vector, the decide vector is this, and the error vector is the difference between the two. So, as I said before, V error vector equals V 2 vector minus V reference vector, which I can write it as VDC angle 60 degree minus V reference angle theta s. I am taking this alpha axis as the reference when I am writing those equations here. Alright. So, let me go further. I can write my VQ tilde and VD tilde as before, and what is VQ tilde? VQ tilde is VDC times cos of 60 degree minus theta s. This is the component of the applied voltage vector. Applied voltage vector is VDC cos 60, along the q axis this is the vector that is applied. So, minus V reference, this is the VQ tilde vector, the applied component minus the desired component, and then what is VD tilde? And VD tilde is basically you have along the d axis. So, what it is applying is you have something applied along the q axis. So, that is nothing but minus VDC sine of 60 degree minus theta s, right. So, this is what it is now. So, you have VQ tilde and VD tilde. We did this in the last class also. I am just having a quick recap on that. So, because what we are going to do is we are basically going to integrate these vectors now, and that is going to be the stator flux ripple vector, which is a measure of current ripple vector. So, let us get going with that. So, this is stator flux ripple vector, and I have done this in the stationary to synchronously reference frame. There are 2 frames, and we are just choosing the DQ reference frame to do the analysis here, because the benefits will be a little apparent when we want to calculate the RMS current ripple little later. So, if you just to have a quick recall of the transformation between the alpha, beta and the DQ, what you can look at is you can say that this d axis voltage, if you have any, that will be V alpha times cos phi plus V beta times sin phi. So, given V alpha, V beta and phi, this is what you have now. Similarly, you have VQ, VQ is going to be V beta times cos phi, and if you take V alpha, so V alpha would have minus V alpha sin phi as the component along that. So, V alpha, if you resolve it along that, you can do this and like this. So, these would be the 2 components of V alpha. So, this is V alpha cos phi, and this will be minus V alpha sin phi. That is what I am written now. So, given V alpha, V beta and sin phi, V alpha, V beta and this angle phi, you can compute VD and VQ. The same way, you can very easily write the inverse of this transformation. Given VD, VQ and phi, you can compute V alpha and V beta. So, you can move from the stationary reference frame to the synchronously revolving reference frame, or back from the synchronously revolving reference frame to the stationary reference frame now. So, this is let us just skip this, because we have primarily been able to cover this in the previous cases themselves. So, these are the error voltage vectors which you can look at in both the frames now. So, now let us go on to the stator flux ripple vector. So, the stator flux ripple vector is something like this now, excuse me. So, what we need to do is we have to integrate the error voltage vector. So, as we saw, the error voltage vectors, if you really want to just look at it, the error voltage vector is sometimes the negative here, the negative of V reference, and when null vector is applied, and it is V 1 vector minus V 2 vector when V 1 vector is applied, and it is V 2 vector minus V reference vector when active vector 2 is applied. So, what is going to happen is in a subcycle you are going to change, you are going to apply the null vector first, and then active vector 1, active vector 2 and again the null vector, or the reverse fashion. So, this is what you are going to do, and therefore, your state of flux ripple vector is going to change in a particular fashion. So, let us get started with that. So, let us say let us define this axis this all right. So, let me say that this is a reasonable representation of the q axis, and let me say this is the d axis at an angle of 90 degrees. Now, instead of drawing d axis here, I am just taking the origin is here just for convenience to draw. First, what is your error vector? The error vector is when null vector is being applied. Therefore, what happens is, let me just change over to the other color, right. When 0 vector is applied, your error vector is like this, and this is when 0 is applied. This is what your error vector is minus V reference vector, or if you look at if you recollect it, VQ tilde is equal to minus V ref and VD tilde is equal to 0. So, for this you get your error going around like this, something of the sort. Now, after that, let us say you apply your 1. So, let me also make this clear as VQ 0 tilde and VD 0 tilde. Why am I saying this? This is VQ tilde corresponding to the null vector or the 0 state 0 being applied now. The next time when I do that, the error voltage vector is along this, it is V1 vector minus Vref vector. So, whatever I will have, let us say this ends here, is going to go something like this. Is going to move like this, as I discussed in the last class. This is going to be parallel to that. So, ignore my drawing inaccuracies, and finally, this is your other error voltage vector, and this man will move parallel to that, and you will come back to the origin. So, this is 1, this is 2, this is 7. Let me just tell you again. So, this is the origin of the dq. So, the time is 0. This is the starting instant of the subcycle duration. The first tz by 2 seconds in the subcycle, you are applying the 0 state minus minus minus. When you are applying the 0 state minus minus minus, you are applying the null vector, and the desired vector is Vref vector. So, what is the difference? V null vector minus Vref vector, which is actually minus Vref vector. So, the error voltage vector is minus Vref vector, and you integrate that, you get a vector which really grows like this. You integrate that, you really get a vector that grows like this. Now, this is at the instant tz by 2. Let me write that down. This is at the instant 0.5 times tz. Then beyond that, what happens? The reference vector, let me call this as psi tilde vector. When I integrate that, what I get is the stator flux ripple vector. So, that is what I am calling as psi tilde vector now. So, this vector, the tip of the vector, once I go on doing the integration, the tip of this vector moves parallel to this error voltage vector 1. So, as I said, just ignore my drawing inaccuracy. So, just you can follow this error voltage vector, it goes on like this now. And subsequently, what happens? You are applying, this is at this instant, this is at the instant 0.5 tz plus t1. Then between 0.5 tz plus t1 to 0.5 tz plus t1 plus t2, between these two duration you apply the active state 2. Therefore, your applied voltage vector is here, the desired vector is here, and this is your error voltage vector. And this error, so now your tip of the vector, you are integrating the error voltage vector. So, the tip of psi tilde vector moves like this and reaches this point at 0.5 tz plus t1 plus t2, and subsequently when you apply the error voltage vector, it moves back in this direction now. So, if you see that this, this base is equidistant in this side, this vertex of the triangle and this vertex of the triangle are equidistant from this origin, which you may call as O or so. Now, this is the case with the conventional space vector PWM. If you are using, let us say, something like sine triangle PWM or some other third harmonic injection PWM and so on and so forth, what will happen is, you will generally, that is within the limits, that is sine triangle PWM is applicable only up to certain amount of fundamental voltage, let us say consider within that limit. So, what would actually happen is, it will just move a little parallel, that is, let me take like this. So, T0 may get shortened and T7 may get lengthened because of common mode addition. If it happens like that, what will happen is just this will move like this and this will move like this, and it will anyway come back to the same point. So, this what I would try to show in the dashed line is the case when the 0 state division is unequal. This is when the 0 state time is equal. So, you can get a feel for this right now, that if the 0 time is equal, then this peak value and that peak value are equal. On the other hand, if the 0 state times are unequal, then this peak value and that peak value are actually greater than that. That is, I mean, this peak value is lower, but this peak value is greater. That actually means that the RMS value of this ripple along the q axis is higher. This is just a point that I am trying to make still qualitatively, I would say that why conventional space vector PWM is better than sine triangle PWM in terms of harmonic distortion. The reason is this, that is, you have this unequal divisions, and I will stress on this point probably in the next lecture more, when I would like to discuss certain alternatives to conventional space vector PWM, and I would say how they are different. But for now I am just making this simple point. You can see that there is an error in the q axis ripple, and the peak value of the q axis ripple is more, and therefore, the RMS value of q axis ripple will also be more. When you add when to sinusoidal PWM, you had 1/4 third harmonic injection. What happens is, it becomes very close to conventional space vector PWM. The division of null vector time is almost equal, and therefore, you get the same thing as the red one, and that is the reason why when you have a third harmonic injection whose amplitude is 1/4 of the fundamental, you get your THD is minimized, but that is not the case when, let us say, you have 1/6 or some other third harmonic, when the ratio, when the percentage of third harmonic added is something other than 25%. Alright. So, let us just stick back to our conventional space vector PWM for the time being now. So, this is how the error voltage vector is. So, I have just shown the trajectory of this error voltage vector along the q axis and the d axis, and now it is time for us to break that into the d and q axis components. So, let us do this again now. So, what I will do is, I will first draw this. Now, let us say this is the q axis and then this is the d axis, and I am trying to reproduce that stator flux ripple vector trajectory that I had drawn previously. So, let me just change the ink color to something else. Now, let us say what we had was something like that. What we had was something like this. So, this is when the 0 state 0 is applied, this is when the 0 state 1 is applied, this is when the 0 state 2 is applied, and this is when the 0 state 7 is applied. Now, what I am going to do is I am going to resolve them into the d axis and the q axis components against time now. The time information is kind of hidden in this diagram. So, I am going to plot the d axis ripple and the q axis ripple against time now. So, let me just get started with that now. The d axis ripple is a little easier to draw, therefore, let me first take that d axis ripple first. I am calling the d axis ripple as psi d tilde. This is the d axis component of the psi tilde vector. Now, this vector that we have plotted here, we will call this the psi tilde vector, that is the d axis component is this now. So, the initial time when the 0 state 0 is getting applied, there is no change in the d axis ripple, there is no change in the d axis ripple. Then subsequently, for certain duration of time, when active state 1 is applied, the d axis ripple changes and changes linearly and reaches some value like this now, and subsequently when active state 2 is applied, it falls like this and then it is 0 here. So, this I would call as T0, this is T1, this is T2 and this is T7. Of course, this is the time for which 0 state 0 is applied, T0, T1, T2 and T7, right. I have drawn for the 4 different durations, and this also should be a straight line. Let me try making this closer to a straight line. Okay. So, it is almost a straight line, it falls like this. Why are these straight lines? Why are these straight lines? This is a straight line, that is a straight line. Why is that? Because this is the integral of V d tilde. What is that? It is some value we had got in the previous one. What is that some value? It would be something like V reference sine of 60 minus theta. So, that is what it is now. So, that is a constant value, it actually changes, but we are now considering over a small interval when the q and d axis are wherever they are, and so there is no change in the reference vector. And now, so the applied voltage, what you are looking at is the difference between the applied voltage vector and the reference vector. So, now the and that you are resolving along the d axis and the q axis component now. So, within this interval the error voltage vector is unchanged, it has a d axis component and some q axis component, the d axis component is 0. And within this interval t 1, again your error voltage vector is constant, though it is different, it is v 1 vector minus v reference vector, and it has certain d axis component, and that d axis component is the slope that you see here. And again in this interval the error voltage vector is constant, it is equal to v 2 vector minus v reference vector, it has a d axis component, that d axis component is a constant now, and therefore, you get it as a straight line, while it is increasing here, it is decreasing here. So, v d tilde is positive here and v d tilde is negative here, and you come back to this now, and it reaches some peak value, right, some peak value it reaches, and let us probably call that peak value as some capital D. Let me call this as some capital D. All right. Now, let me try and go and plot this is versus time, this is versus time. Let me plot psi q tilde. How am I going to get psi q tilde? So, let me just project all this down. Okay. So, now what happens is when I start from here, when I apply null vector, psi q is 0 and it actually goes in the other direction, it actually goes in the other direction. Then when I apply active vector 1, then v q tilde is actually positive and it goes about increasing at something like this. Then when I apply active vector 2, v q tilde is a small positive value for the specific case we have considered, and it changes like this now. And subsequently when the other 0 vector is applied, that is t 7 0, I mean the 0 state 7 is applied, this falls like this, it comes down to this now. This is what we have. So, psi q tilde has a variation as shown here. So, now we can give some more values to this now. What are those values? So, let us say we call this, let us project this, that is what, that magnitude of this is actually V reference multiplied by T z, V reference multiplied by T z, or it is actually minus V reference into T z now. Let us define some quantity which is called this Q z is equal to minus V reference multiplied by T z. What is the significance? We are talking of the interval when the 0 vector is getting applied and the error vector is minus V ref when 0 vector is applied, and 0 vector is applied for a total duration T z. So, this is error volt second difference now, and what you have here is this T 0 is equal to 0.5 T z, and therefore, this is going to be 0.5 times Q z, this is going to be 0.5 times Q z, all right. Then you have other one, that is you have this quantity, you have this quantity which is the length of the other side of the triangle. What is this length of this triangle? This is again the error voltage vector. So, what is the error voltage vector corresponding to this side? It is V 1 vector minus V reference vector, that multiplied by T 1 is the length of this particular triangle. So, if you look at its q axis component, its q axis component is something like q 1 is V d c cos of theta s minus V reference times T 1. So, what would be your q axis value at the end of it? It will be 0.5 q z, 0.5 q z plus q 1, that would be the value there now. Again you take this one, there is another side of the triangle. What is that side equal to? That corresponds to the state 2. So, there is the error voltage vector is V reference minus V 2 vector, I am sorry V 2 vector minus V reference vector multiplied by T 2, that is what is this time, and its q axis component you can call this as q 2 would be V d c cos of 60 minus theta s minus V reference, that is the error voltage component along the q axis, that multiplied by T 2. So, this value you have here at this instant is 0.5 q z plus q 1 plus q 2. I am just trying to fill in numbers for this, and finally, it becomes 0. So, what I have shown is I have shown you the nature of variation of psi d tilde and psi q tilde for this particular V reference and alpha. If you change that V reference and alpha, I have considered some value of V reference and alpha which was here, this V reference and this angle theta s. If I do not consider that, I will get something else. So, I will do this. If I mean this triangle will be different and the d axis and the q axis components are different. So, for a particular example we have evaluated now. The nature of variation is shown here. You can see that this is a piecewise linear curve and the slopes in during the null vector are equal and the other slopes during the other two intervals are different now. And psi d tilde is also piecewise linear, but psi d tilde is 0 during the intervals whenever the 0 vector itself is getting applied. So, this is just to get some idea of the d and q axis components of the stator flux ripple vector, and these are also the d and q axis, they correspond to the d and q axis, the current ripple vector now. So, let us say how would you get the RMS stator flux ripple over a subcycle? That is an important question now. How would you get the RMS stator flux ripple over a subcycle? Let me go over and do that figure again now. So, let us say that I have this d axis and the q axis things. So, let me call this as psi d tilde and I will call this as psi q tilde, right. So, let me just choose a different color. Now, what I had was, this was something like this was the nature. This was the nature of my d axis ripple and this is some capital D. And what is this capital D? This is actually the d axis error. What would be the d axis error? Something like VDC sine of theta s would be the d axis error multiplied by T1, that is the d now. So, if you take the q axis, the q axis ripple is something like this, the q axis ripple is something like this. I am trying to reproduce that here, and we also found out the values at the various switching instance now. What I want to do now is the root mean square value. I want to get the root mean square value. For the root mean square value, what I should do? I must first square the function, then I should take the mean value of the function, then I should take the square root of the function now. So, first let us square the function. How can I square the function? Let me choose a different color ink, right. So, now I am going to square the first function. What happens if I square that? Psi d tilde is 0 here, so I am going to square it is 0. Again it is 0 here, so when I square it, it is going to be 0. What happens in between? So, this is a straight line, whereas the psi d tilde is going to vary like a parabola. It is going to vary like a parabola. And similarly, here in the next interval also it varies linearly. So, it will be a parabola like this. This would be the nature of psi d tilde squared. I am writing psi d tilde square in green color ink, so that we know what I am doing now. Alright. Next, what am I doing? I am going to consider psi q tilde squared. So, if I square this, I am going to get a parabola like this. If I square this, what do? I will once again get a parabola. Let me just draw this a little better. Okay. Okay. So, I will square this, I will get a parabola like this. The next time I square this, I will also get a parabola. I will get a parabola which would be something like this. Now, I will get a parabola which is something like this. Then the subsequent one also would be a parabola, and that is a section of a parabola like this, and here again there will be parabola which goes down this knot. This is how the nature of variation is for psi q tilde squared. So, these two are actually equal. There is just my drawing inaccuracies, because if these two are actually equal and opposite in sign, they are supposed to be, and so this will also be equal and opposite to that now. So, why am I doing that? I am just first trying to get a feel for the to calculate RMS value, how you have to square that. I am just trying to square. So, the psi tilde and psi q tilde, or id tilde and iq tilde for that matter, are piecewise linear functions, and if you square them, they become piecewise parabolic functions. They are all parts of some parabola or the other over the different intervals of time. So, now we just have to handle this. What we need to do is we have to calculate the mean value of this. So, that is basically you have to calculate the area under that. To do that mean we need to integrate that, right. So, we have to calculate the area under this parabolic sections, which is what I had briefly indicated, the some basic idea behind that in the last class. So, let us say you have a straight line like this, which passes through the origin. This is x, this is y. So, if you square this line, what happens? You will get a parabola which is like this, which would be symmetric on both sides of x axis like this. Now, it does not look symmetric, let me just clear that up. All right, let me redo that. So, this will be flat 0 and the slope will also be 0 here, and this would be symmetric on both sides like this. This is how it will be now. Instead, let us say if I take a different parabola, that is if I take a different straight line, that straight line let us say passes here. This is the different straight line. If I square this, so what will happen? I will once again get a parabola, but that parabola will be like this, will be something like this now. So, what we are looking at is the area under the parabola. So, now let us say if I have a parabola like this is y and this is x, and now what I want is this is some value of x1, this is the corresponding value y1, and I want the area under this parabola. This parabola is of the form y is equal to x squared or kx squared, or y is equal to ax squared. So, I want this area under the parabola. So, what is the area under the parabola? As I told you the other day, area that is shaded is 1 by 3 times area of rectangle. Which is the rectangle? Let us call as O, A, B, C, of this rectangle O, A, B, C. So, it is very easy to see y is equal to x squared. If you integrate this, x cube by 3, and x cube is the area of this is x1, this is x1 squared, or whatever. Let us take the simple case of y is equal to x squared, this is x1 squared. So, the entire area of the rectangle is x1 cube, and now the shaded area is x1 cube by 3. So, it is very easy for us to see that. That is true when you have the parabola somewhere else also, like for example, if you take the x axis and the y axis being here, and let us say you have a parabola like this, and now we are looking at this shaded area. This is the axis of the parabola, this is you are looking at this shaded area. Once again you can construct this rectangle. So, the rectangle, one of the sides of the rectangle is the horizontal axis, the other side of the rectangle is the axis of the parabola, and the other vertex is given by the point that you are interested. So, this area of this rectangle and the shaded area is once again, the shaded area is 1/3 of that area of this. So, it is very obvious, right, you are just shifting that. So, there is nothing else, you can prove this also mathematically now. So, this is the idea which we are going to use now, and you get parabolic sections by integrating or squaring the linear sections. But what kinds of parabola? You are having a straight line that intersects at a particular value of x. So, it has a particular root and you are squaring. When you square, you get a parabola, and the parabola is going to have real roots and equal roots. What is that root equal to? Wherever it intersects the horizontal axis. So, these kinds of parabola have real and equal roots. If they have x1, x2 are the roots, you will have x1 is equal to x2, where there are, these are the roots of the parabola. So, you will have real and equal roots for the two parabolas now. So, that is the kind of parabola that you will get whenever you square these kinds of straight line, and that is what we will be dealing with now. So, there are lots of things which are actually I can give you in a reference here, but before that let me just do a generalized thing. Now, you may be wondering about this question, how do I formally prove that that shaded area is equal to 1/3 of the area of the rectangle, and how I can use it now. Let us say I take the straight line y is equal to mx plus c. I take the straight line y is equal to mx plus c. Now, what I want to do is I want to evaluate the area under the parabola. I am first squaring that line mx plus c the whole square. Then I am going to integrate it with respect to x dx. I am going to do it between some values x1 and x2, and this is what I am planning on doing now. So, what do I get here? That is, let us say I have a straight line like this. So, some straight line, this is some straight line. I have points x1 and I have a point y1, sorry, this is x2, sorry, yeah, this is x2 and the corresponding points are y1 and y2. Now, I am going to square this to get a parabola. So, this is what I am trying to do. So, mx plus c the whole square I am doing. This is what I with respect to dx, and I am trying to evaluate them with respect to dy. So, what do I get here? If I integrate this function, it is going to be mx plus c, which is the equation of the straight line that I am squared. So, that I am integrating this, it is going to be mx plus c the whole cube divided by 3m. This is evaluated, you know, in the interval x is equal to x1 and x is equal to x2. So, what is mx plus c if you look at? What is mx plus c if you look at? Mx plus c is nothing but y1 at x is equal to x1 is y1, the other one is y2. So, this is effectively it is 1 upon 3m multiplied by y2 cube minus y1 cube. So, what you can do is you can write this as y2 minus y1 divided by 3m multiplied by y2 squared plus y2 y1 plus y1 squared. So, this what is y2 minus y1? It is actually there is mx2 minus mx1 actually. So, this itself reduces to x2 minus x1 divided by 3 multiplied by y2 squared plus y2 y1 plus y1 squared. So, this is the expression we will use when we are going to have any linear section like this. We are talking of any linear section like a straight line between x1 and x2. We want to square that and evaluate that. This is the expression that we will use now. So, you can refer to this MSc engineering thesis by Mr. Pavan Kumar Hari on comparative evaluation of space vector based pulse width modulation techniques in terms of harmonic distortion switching class. You can particularly look at chapter 3 for this reference, where you know in this where this question of RMS state of flux ripple over a subcycle is discussed, and particularly a discussion on these kind of areas under the calculations, and where the details of the calculations that I am presenting here are available here with regard to RMS state of flux ripple over a subcycle now. So, if you want to look at the d axis ripple over a subcycle, it is fairly easy process now, whatever we have derived. So, the d axis ripple is of this nature. It is like this, it rises and it falls and it comes back. This is the whole time Ts. So, this is I mean let me just draw that a little symmetrically here. Okay. So, this is T0, this is T1, T2 and T0. Here it reaches the value D. This is psi d tilde. So, when I get the RMS value here it is 0. So, this RMS value, what do? I am just going to square. So, when I am squaring, it is 0 here and it is parabolic here, and again it is a parabolic thing here, and it is like this now. So, this area under this parabola is 1/3 of this area of the rectangle. So, this whatever is, I can use the same, this shaded area is 1/3 of that. The same way this shaded area is 1/3 of this area of this rectangle. So, I can write this value as 1/3 times d squared multiplied by T1 plus T2 divided by, this is the total period of time Ts. This is like my mean square value of that, and you can see it is fairly simple. And if I take the square root of this, I am going to get the RMS value. So, it is very easy. T1, T2 are all functions of V reference and alpha, V reference and theta s and so on, and D is also a function of all of them now. So, you can see that D is equal to VDC sine of theta s multiplied by T1. And what is T1? T1 is V reference sine of 60 degree minus theta s divided by VDC sine 60 times Ts. Similarly, you have T2 equals V reference sine of theta s divided by VDC sine 60 theta. These are things which we did earlier in the earlier classes. So, you can see that everything is a function of just 3 quantities V reference, just 3 quantities V reference, theta s and Ts. So, the entire thing is a function of V reference, theta s and Ts. So, this is the RMS d axis state of flux ripple. The RMS q axis current ripple is a little more complex, but let us not worry, we will do that. You will see that once again what you will see is in the RMS q axis current ripple also would turn out to be a function of V reference, theta s and Ts. So, let us just get started now. So, this is the calculation of RMS q axis ripple over the first subinterval. I am just doing it subinterval by subinterval. So, let me take something like this now. What is the first subinterval? This is 0 and this is 0.5 Tz. It is changing like this and this is going to a value 0.5 times Qz. So, when I am squaring it, it becomes a parabola like this, and the area under this parabola is, that is the shaded area, is 1/3 of the area of this rectangle. So, what I can say here is it is going to be 1 by 3 times 0.5 Qz the whole squared, 0.5 Qz the whole squared multiplied by 0.5 Tz, that would be the area of the rectangle, and this is going to be 1/3 of that now. This is what you are going to get now. So, let us call this by some value. What thing shall I give? Let me say this is small q1 is this. So, this is the mean square value we are trying to calculate now. So, this 0.5 Tz I can divide it by the overall time Ts in an effort to find out the mean square value now. So, I am just trying, I am finding the contribution of the first subinterval alone towards the RMS q axis state of flux ripple. If I consider the second one, how is the second one? If I look at the second subinterval, so this is the first subinterval where you minus 0.5. In the second subinterval it increases like this. You just recollect the psi q tilde graph that I had drawn before, and this is 0.5 Qz and this is 0.5 Qz plus Q1, and this is the time interval is T1. So, if I am going to square that now, so what I am going to do? I am going to square this. When I square this, I will get a parabola, and that parabola will be sitting here. I am going to get a parabola like this now, and there is this area under this parabola. This we had just found out the earlier expression. How to get this now? That is, what you do is you have this 0.5 Qz, you square it, then plus 0.5 Qz multiply by 0.5 Qz plus Q1. Then what do you do? Plus 0.5 Qz plus Q1 the whole square. So, this is, I am just following what we did before, by squaring the linear section. I am going to take 1 by 3 Ts of this and multiply this by T1. Now, this is going to be the contribution of the second subinterval to the mean square q axis state of flux ripple. These are the mean square values I am just trying to compute now. The same way, if you go to the third subinterval, and the third subinterval, it will look like this now. It changes like this and then it is going up. Then the third subinterval is what we found in the specific example was more or less flat. This is T1. Here you have the value 0.5 Qz plus Q1. Here you have the value 0.5 Qz plus Q1 plus Q2. You will interestingly find that this whole thing is equal to minus 0.5 Qz. Minus 0.5 Qz, because Qz plus Q1 plus Q2 should add up to 0. So, you will find that is that. So, if I do the same kind of an expression as before, what I will get is I will get T2 upon 3 times Ts multiplied by 0.5 Qz plus Q1 the whole squared. I am trying to evaluate the area under the parabolic section using these values, using these two values now, plus 0.5 qz plus q1. I am going to multiply this by minus 0.5 qz, then plus minus 0.5 qz the whole squared. This is going to be the contribution of the third subinterval to the mean square q axis stator-flux ripple. Now, how about the last subinterval? The last subinterval is kind of very similar to the first subinterval. So, this is 0.5 qz, the last subinterval it is minus 0.5 qz, from here it is 0, this value is 0. So, this duration is again Tz by 2, and this is psi q tilde I am talking about. I am now going to integrate psi q tilde. So, if I integrate here, I am going to get a parabola like this. I am going to get a parabola like this now. I am going to evaluate the area under this parabola. So, what is that going to be? It is 0.5 qz. You can even take the minus 0.5 qz and square that, multiply this by Tz by 2 or 0.5 Tz, correct. That is the area under that rectangle and 1/3 of this, and this I would call as q4. The previous one I can call this as q3, this previous one I can call this as q2, and this previous one is q1 now. So, I have got the mean square values in the various subintervals now. So, what I just have to do is I will have to add q1 plus q2 plus q3 plus q4 to get what? The mean square value, to get the mean square q axis value. This I can always take it under a square root, and I am going to get the mean square value under that. So, let me just call this as psi q RMS if you wish. So, psi q tilde RMS I am going to get like this now. The psi t tilde RMS is something which we got even earlier, that was more or less a straight thing that we had found before, which is basically 1/3 of d squared T1 plus T2 by Ts. So, this is my psi d tilde RMS. So, psi d tilde RMS is as we calculated before. So, this is 1/3 d squared T1 plus T2 root 2s, the whole thing under square root now. So, what is your psi tilde RMS squared? That is psi q tilde RMS squared plus psi d tilde RMS squared. You can just add the two and you will get the RMS stator flux ripple over a subcycle. You can look at the thesis, there are also other references. This thesis is one good reference where this has all been explained in a fairly clear manner now. So, you will find that the d axis flux ripple, the psi d tilde RMS we found is a function of V reference, theta s and Ts. Similarly, you can also see that psi q tilde RMS is also a function, though a different function of V reference, theta s and Ts, and therefore, the whole of psi tilde RMS is also some function of the same 3. You will see that, and this has been evaluated, and now you will see that this is, it will actually interestingly it is of the form C0 Vref squared plus C1 Vref cube plus C2 Vref power 4, the whole thing multiplied by Ts squared. So, this is your psi tilde RMS squared is generally is of this form, where you see that this is the function of dependence on Ts and so on. So, let us look at the remaining things in the following lecture. So, this is just to show how this the dependence on all the 3 things now. So, I look forward to your this thing in the next lecture, where we will discuss further details on this calculation and do the other PW methods. Thank you very much.